All right. So, when we have a chemical reaction and we want to kind of talk about the kinetics of the chemical reaction, meaning, again, the rate at which a chemical reaction occurs, we have something that's called the rate law. The rate law. All right? And the rate law always looks something like this. So for chemical reaction, A plus B going to some products. Now notice we don't have to actually identify what the products are because the rate law, the rate of the chemical reaction, doesn't need to have the products in it. Okay, so again, when you write the rate law for a chemical reaction, the products aren't in it because the rate, how fast this reaction occurs, how fast A and B combine to form products, what is it dependent on?
You said temperature, right?
Okay, temperature is one thing.
Catalyst, if there's a catalyst.
Very good. Catalyst, if there's a catalyst in the reaction, that'll lower the activation energy and speed up the rate. What else?
Surface area, right?
That's right, surface area. And what's the major contributor?
Oh, concentration.
That's right, concentration of A and concentration of B. The more A and B, the easier it is that they can find each other and the reaction can proceed. Does it matter how much products we have, whether or not A and B react?
No, yeah, that doesn't matter, right?
That's right, good. So the rate is proportional to the, and these little brackets mean the concentration of our reactants A and B. And the rate of a reaction is also proportional to the concentrations of A and B, but A and B raised to certain exponents, which we call the order of the reaction. So this is a typical example for a rate law. You write the word rate, so rate equals K, there's a constant, and that constant will depend on just the chemical itself, the different kinds of parameters, the temperature, for example, the reactivity of the chemical, times the concentration of A raised to order times the concentration of B raised to an order. All right? These orders, these units for A here and B here, concentration, are going to be generally in molar, right? Molar, that's the concentration, moles per liter. All right? With the rate of a reaction is always going to be in order in units of molar per second. Okay? So again, the rate of a reaction is always going to be in units of molar per time, and usually it's seconds. Okay? Good. Okay, so the rate law for this reaction here, 2A plus B yielding 3C, is, and again, rate laws always look like this, rate equals 0.045, and then, now this is the K, so let me again draw the, we don't have it here in front of us, it was on the previous slide, so let me write a generic rate law, which looks like this. Rate equals K times concentration of reactants, A to the X, and in this case our other reactant is B to the Y. All right, so this is an example of a rate law, and the one that they tell us for this reaction is the rate is 0.054, that's our K, times the concentration of A times the concentration of B. If the concentration of A is 0.2 and the concentration of B is 0.3, we can identify what the rate of the reaction will be, right? We throw in here 0.2, we throw in here 0.3, multiply that by 0.045, and that will tell us the rate of the reaction. And again, the units for the rate are always going to be in molar per second. And we can see that this is molar and this is molar. And the units for our K value here were in 1/m per molar per second. And so if we write that out, again, the units for our K value were 1 over molar seconds. And A, its units, were in molar. And B was in units of molar, right? Those are concentrations there. So molar times molar per second, cancel out. And we have 1 over, no, we have molar that's going to be on top, and then per seconds. So again, the units for the rate are going to be molar per seconds. And the units for K will change based on the rate law. But given the rate law, you can know how fast a chemical reaction will occur. And if the chemical reaction is not dependent on the concentration of material, for example, if I have a chemical reaction like this, where A goes to B, and A just turns to B, it doesn't have to react with another A, or is not dependent on how much B there is. It's just decaying to B, decomposing, right, to B. And so the rate law for this would just be rate would equal K, and that's it. The rate is not dependent on the concentration of A necessarily. And so the rate would just be equal to your K value. And in this case, the K value would have to have units of molar per second, because again, rate is always in units of molar per second or molar per time. And usually, again, we're going to be dealing with seconds in this chapter. Okay. So, how do we determine the rate law? If I give you some random chemical reaction, 2A plus B yielding C, all right? How do I determine the rate law? I can draw the skeleton rate law very easily. Again, the skeleton is just rate of this reaction equals K, some constant, times the concentration of A, times the concentration of B, where these are raised to values, X and Y. But that's all I know. I don't know what X and Y are, and I don't know what K is. Okay? X, some people want to say, oh, X is going to be 2. But that's not the case. X and Y are independent of my coefficients there, right? Independence of this stoichiometry here. So I don't know. They might, X and Y might both be 0. And this reaction might depend only on the K, the rate constant. Okay? So, how do we determine the rate law? We can write a skeleton rate law for any chemical reaction provided. But when we say how do we determine the rate law, what we're saying is, how do I find out what X and what Y and what K are in this rate law? And now again, going back to this, anytime you have a rate law, what you can do with that rate law is put in the necessary concentrations of A and B, and you'll know how fast the reaction will proceed. And oh, we didn't say this. The rate law is determined by experimentation. What we do is we combine a known amount of A with a known amount of B, see how fast the rate law is, how fast the reaction proceeds. And then we change something. Maybe we say a known amount of A with twice as much B this time. And we see if the rate law doubles, right? And from that, we can identify what these values are. And then ultimately, after we have these values, we put in a known concentration of A and B, find the rate, and we can solve for K. All right, so the reaction order, again, is with respect to a given reactant. So if I say the reaction order for A, and the reaction order will always be this exponent. So right now we don't know what it is, but the order with respect to A for this reaction right now is X. The order with respect to B for this reaction is Y. If I perform chemical reactions and I find out that the rate law is 16 per molar per seconds, right? And concentration of A to the 1, concentration of B to the 1, all right, then I can say that the rate of this reaction, because I have a complete rate law here now, is first order with respect to A and first order with respect to B. All right, if there's a 0 up here, that means it's first order with respect to A, 0 order with respect to B. And again, if this might be a 2, then you would say it's second order with respect to A, 0 order with respect to B. Now, what does that mean? Well, it just means that you can see the rate is dependent on these concentrations. If it's second order, the concentration of this will change the rate of this law twice as much. If it's 0 order, you change the concentration of B. Do you remember what happens if you take a value and raise it to 0?
Z equals 0?
No, if I say 5 to the 0, that equals what?
I can't remember.
5 to anything to the 0 always equals 1. All right? So if you take a value and raise it to the 0, it doesn't matter what that value is, it's always 0. So if you double the concentration and the rate doesn't change, that means that the rate of this reaction, the order of this reaction with respect to that concentration is 0. All right? In other words, its concentration does not affect the rate of the reaction. And usually you won't leave that in the rate law. So, because of that, if you have a 0 order reaction, the units for K will be different than if it's a first order or the second order reaction. So the units for a 0 order reaction are usually going to be mole per liter per seconds. For a first order reaction, it's just going to be per seconds. And the second order reaction is going to be liters per mole per second. Or in other words, mole to the negative 1, molar to the negative 1 per second. Written like this. Okay. So now let's use the rate law, use rate laws to determine the order of the reaction. All right? So we're going to take this reaction and we're going to write a skeleton rate law. A skeleton rate law. Can you help me with this? A generic rate law?
So let me see. To write a rate law, you write rate, right?
That's right. We always start writing a rate law by writing the word rate. And then equals, what does it equal?
K. Now, what are the units on the K again?
You don't have to worry about that right now, but I do want to make sure you recognize that this is a lowercase k. And that'll become important in future chapters. But we want to recognize that it's a lowercase k that we're using. So the rate of the reaction is K, and then what else do I write?
Concentration of A times concentration of B raised to X and Y.
All right, but we don't have to use A and B right now because we have this chemical reaction, right?
Oh, yeah, okay. So concentration of NO.
Concentration of NO.
Raised to the 2?
No, we don't know that necessarily. We just choose X, right?
Okay, yeah.
You don't know the stoichiometry here doesn't necessarily tell you what the order of the reaction is. Sometimes it does, but not always.
Okay, and then times the other reactant's concentration, oxygen, to the Y.
Very good, to the Y. So now what we do is we select 2 of these rate informations. So if I did one experiment, experiment 1, with this concentration of NO, this concentration of oxygen gas, the rate at which NO2 is produced is 0.048 molar per second. So what I do is I plug these values in. I plug this value in. The rate for experiment 1 here is 0.048 molar per second. Right? I'm going to leave out the units just to kind of make it a little bit easier to see. The concentration of the NO here is 0.015. The K doesn't change for different concentrations. We can go back to this one. It says here, let's see. The rate law is unique to temperature and concentration conditions. All right? The rate law cannot be predicted from chemical equilibrium, but must be determined experimentally. Okay. So this isn't true. This is true that the rate law is unique to temperature, but when it says it's unique to concentration conditions, if you change the concentrations like this, it doesn't actually change the K value. All right. So our K value here, I mean, you can influence this K value by extreme changes in concentrations, but slight changes like this aren't going to change the K value. So we don't have to actually put a value in here for K to start off with. All right, so 0.0015 came from this experiment 1 here, and 0.015 came here. Now remember, these are raised to some exponents. We don't know what they are. And then we write a second experiment down beneath here. So we're doing 2 rate experiments here, where this is 0.03 to the x, and this is 0.015 to the y. Now in these 2 experiments, and the rate here is 0.192. So in these 2 experiments, what we see is that as you double not A, but NO, it does something to the experiment. What does it do? How does it change the rate?
Let's see. Is that double?
Well, it's a little more than double, isn't it?
Oh, yeah. Is that 4 times?
I think it is pretty much 4 times. Let's turn on a light here for ourselves. Did I turn on the light? Try it again. Oh, there's the light. Okay. Oh, that's the light. There we go. So, what do we got? 0.0, what are we looking at here? 0.192 divided by 0.048. So the rate is 4 times as fast. So I doubled this concentration, but the rate went up 4 times as fast. And if you think about it, that helps us know about this exponent here. All right? If the K values are the same between these 2, so you can just call these as fixed, then that tells us something about the exponents. Now we could do the math and we could solve for the exponents, but it's a little bit well, it's a little bit intensive in terms of identifying the exponent. But we can simplify it for ourselves. We can simplify it for ourselves by saying that if I take this 0.15 as x, or just we call it 1, all right? So the concentration of my NO was 1. The concentration of my O2 was the same. Again, these are raised to x and y. The rate over here, I'll call 1, all right? And the rate here, I've decided it was 4 times as fast, and this concentration here was twice as much, and this one was the same. Now, with that, it becomes pretty clear. What does the exponent here have to be?
You mean 2 to the whatever?
That's right, because 1 to these values is going to be the same. It's going to be 1. 1 times whatever. 1 times 1, however many times, is going to be 1. So, but 2 here to the what is going to make it 4.
Oh, to the 2.
That's right. And so what that's shown us is that the exponent here is 2. Now it's a little bit hard to see here. You could go through the math and solve for it, and you'd find that yes, it is actually 2. But when you simplify these things in terms of ratios of these materials, then it's pretty easily seen that our exponent on this concentration has to be 2. Or in other words, as you double this concentration, the rate increases from 1 to 4. All right, it increases by 4 times when you just double this concentration, showing us that that exponent again is 2. Okay, so now I can choose 2 other experiments where we maintain the concentration of A and we change the concentration of B. All right, so let me write down my skeleton rate law here. Rate equals, what does it equal?
Rate equals K times concentration of NO times the concentration of O2. Like that?
Yeah, are you missing anything?
The exponents?
That's right, the exponents. And now we know that this is 2, but this one we still don't know. We'll call it y. Okay? So now I'm going to fill in with experiments 1 and 3 and see if I can identify the order with respect to the O2. I've found the order with respect to NO. It's 2. Now I'm going to try to see if I can find the order with respect to the oxygen gas. So if I think of this rate value here as 1, right, and then I can compare 0.96, that's going to be twice as fast, right?
Yeah, 0.96 divided by 0.048 is 2.
So if I say for experiment 1 here and experiment 3, the rate goes from 1 to 2, and my concentration of NO, it doesn't change. It's 1 to 1, and we'll just say this is the same concentration, but here the oxygen goes from 1 to 2, and that helps me identify what the Y is. 2 to some value doubled the rate, right? Doubling doubled the concentration of oxygen gas raised to some value doubled the rate. What do you think? What is Y?
Y has to be 1, right?
That's right. That's right. Y has to be 1. So the result is the rate equals K times the concentration of NO squared times the concentration of oxygen gas to the 1. All right. So after we've done this, and now this is the algebra to help us find the rate with respect to NO, right? And it works exactly the same. And then this is the algebra for doing it for rate 1. This is the non-simplified method, right? After we get this rate law to this point, we can then get a K value by plugging in one of these lines here, any one of these experiments. So for example, NO, I can put in here 0.015 squared for oxygen. Well, yeah, we're choosing experiment 1, so that's also 0.015 to the 1 times K equals 0.048. All right, so I can use my calculator here and solve for K. 0.015 to the third power, because squared times that is 1, and then 0.048 divided by that value there. So that makes K 14,222. So now the final rate law is rate equals, that's our K, concentration of NO squared, concentration of O2 to the 1, and the units here are going to need to, this is going to be molar cubed, so we're going to need molar squared on the bottom to get rid of 2 of those molars. You always need to remove your molars. Where do you go to get rid of molars?
I don't know. What do you mean?
Yes, you need to get rid of molars here, right? Because we have 3 molars on top. We need to get rid of 2 molars. So the rate, because what is the rate always equal to? The units?
Oh, you mean molar per second.
That's right. So where do you go to get rid of your molars?
You just multiply it.
No, you go to the dentist. That's where you go to get rid of your molars.
What? Oh, that's the first good joke I think I've heard you tell.
You like that one?
Yeah, that was a pretty good one.
Okay, good. Yeah, I always save it for this very point. All right, so we need to make sure we can see it's per molar squared per second. And then this is again going to be molar squared. This is going to be units of molar. And that will make it so that these, oh, no, these aren't molars on top. This is molar squared on the bottom. So 1 over molar squared per second. Molar squared will cancel out, and then we'll have molars left on top and seconds left on bottom. Okay, very good. Good place to stop.